Hello everyone, welcome to our course on computer network. So today we'll look into the last lecture of IP networking. So we'll look into certain services on top of the IP network, and we'll see that how those services actually help to support the end-to-end functionalities over a network. So let us start with our lecture today. Okay, so in this particular lecture, we are going to talk about three different technologies which are built on top of IP or which are closely associated with the layer 3 of the TCP/IP protocol stack. So we'll look into details about this concept of NAT, network address translation, and two different IP services protocols, address resolution protocol or ARP, and internet control message protocol or ICMP. So in our theory class, we have looked into the details about the IP addressing, and we have seen that how IP addressing is used to ensure the routing over a CIDR based IP network. So the IP version that we have seen till now are mostly the IP version 4. So the major problem, or one of the major problem of IP version 4 is that the number of IP addresses are limited. So you know that the IP addressing is 32 bits, so you can get a maximum of 2 to the power 32 minus 1, that many number of hosts assigned with that IP addressing scheme. But out of that 32-bit IP address, initially we had this classful, classless based division where certain bits were fixed for the network IP and certain bits were fixed for the host IP. But later we moved towards the concept of CIDR or classless interdomain routing. In CIDR, we have broken up this concept of network IP and the host IP and used this entire 32-bit addressing. And with the help of that network mask, we have divided the network IP part and the host. So that was our broad idea about handling this IP or handling the large number of devices that we have with the help of the IP devices. But still there is a limitation, because out of those addresses, there are certain addresses which are particularly reserved for the research purpose. There are IP address pools which are considered as the private IP addresses that we are going to see from a while in a while from now. That actually limits the total number of IP addresses which are available in IP version 4. But if you look into the number of network devices, the number of network devices are actually growing over time. So nowadays we have these IoT devices where there are small tiny sensors which are embedded on top of a small single board computer. Now all those devices that has a network interface card, that should have an IP address associated with it. So if you want to use the layer 3 or the above layer services in the TCP/IP protocol stack, it needs to have an IP address. So because of that reason, we have increasingly growing number of devices in the network, but that many number of IP addresses are not available in IP version 4. Now to solve this problem, this IP version 6 was introduced. It is not only about the IP version 4 address scarcity, but to handle many other problems which are associated with IPv4. But the major problem of IPv6 is that it is not directly backward compatible with IP version 4. So that is why we have never seen a global deployment of IPv6 over the world. So there are pockets of network which support IP version 6. But widely we still now use IP version 4, which is the 32-bit IP address. Now, the major remedy that has been used or that has been accepted widely across the globe to solve this IP scarcity problem is to reuse a block of IP addresses which are known as private IP addresses. So in every class of IP addressing, in class A, class B, or class C IP address, we have a reserved block of IP address which is known as the private IPv4 address. So in class A, you have 10.0.0.0/8 as the private IP address. In class B, you have 172.16.0.0 to 171.31.0.0 as the private IP address pool. And in class C, you have 192.168.0.0 to 192.168.255.0 as the private IP address. Now, these private IP addresses, they are meant for the private network. For example, if you develop a small network which does not have any kind of global internet connectivity, that means you do not want to send a packet outside your network. You just want to do, say, you have set up a small experimental testbed network and you want to make the devices communicate only among themselves. And it doesn't need a connectivity with your outside network. So that here you can use actually this kind of private IP addresses. And initially these private IP addresses were developed for this particular purpose. Now, because in such a scenario, there is no global connectivity or there is no connectivity with the global internet, this block of IPv4 addresses are reusable. So for example, if you have two different networks, both of them are the private network and they are not connected to outside internet, and at the same time they are not connected with each other, then you can reuse the same block of IP addresses in both the network, because they will only talk internally and they are not going to talk with the outside network. Now, a network interface must have a public IP version 4 address to communicate with the global internet. Why? Because we need to enable routing of the data packets towards the proper destination. So typically, this hierarchy of IP version 4 addressing is used to route a packet over the global internet. So that is if you want to connect your devices with the global internet, or if you want to connect your subnet with the global internet, you should have an address pool, or you should have a public IPv4 address that is visible to globally to all the devices such that routing can be enabled. Now the question comes that how we can use, or better to say, reuse this block of private IPv4 addresses to solve the problem of IPv version 4 scarcity. Now here is an example. The way we are actually moving forward of reusing this IP version 4 addresses. So the idea is that you create the pocket of subnets with reusable private IPv4 addresses. For example, you use the private IP version 4 addresses within an organization. So you have three networks here: the IIT KGP network, the IISc network, and the IITD network. Now all these three networks can use the same block of IP addresses. So they can assign the IP addresses to the devices from the block of IP addresses 172.16.0.0/60, which is a private IP address block in class B network. So the same IP addresses can be reused in all these individual organizations. But then comes the question that how these organizations are actually going to talk to each other, or how they are going to connect to internet. Because if you are using the private IP addresses to the devices which are within this organization, that devices will not be able to communicate to the outside network unless it has a public IP interface. Now here, one of the interesting observation is that not all the users in an organization are active simultaneously. So if you look into the users who are there in IIT Kharagpur network, we have a large campus. Indeed, we have a very large campus with around 10,000 residents within IIT Kharagpur network. So ideally, we should need 10,000, at least 10,000 different public IP addresses. Many of the people, they have more than one devices connected to the internet, so they might need more than one public IP addresses. But if you look into the user behavior or user activity pattern, it is not like that all the time, all 24 hours in a day, all the 10,000 users are going to access internet at the same instance of time. So typically at an instance of time, only a fraction of the users, maybe 20% or 30% of the users are active who are actually using the internet. Others are not using the internet at that point of time. So that means to communicate with the outside internet, you only need a public IP interface for those active users. Now, here comes the interesting concept of network address translation, which is basically used to convert these static private IP addresses, which are assigned to all the devices within an organization, and map it with a corresponding public IP address. So here is the solution. So you map the private IP addresses of the active users to the corresponding public IP addresses of the individual network. Say here, I have taken example of 3 different users, 3 different active users in these 3 different networks. So in IIT Kharagpur network, I have an active user who has a public IP of 172.16.10.2. In IIT Delhi network, I have an active user who has just a private IP 172.16.10.19. And in ISC network, I have another active user 172.16.10.2. Now, as I have mentioned, that the same IP block of IP addresses can be reusable. So you can have the same user, or you can have 2 different users in 2 different networks having the same private IP address. So here, the user at the IIT Kharagpur network, it is an active user, and that user has an IP of 172.16.10.2. And at the same time, another active user at the ISC network, it has the same IP address 172.16.10.2, which is always possible. Now, the idea is that when these active users are going to communicate over the internet, we are going to assign a public IP to those active users. So that means when this user, active user within IIT Kharagpur network, which has the private IP of 172.16.10.2, and it wants to send the data packet to the outside internet, it has been assigned a public IP 202.141.816. Similarly, when the active user within ISC network has the private IP 172.16.10.2, it is communicating with the internet, it has been assigned a public IP of 202.141.88.9. Similarly, the IIT Delhi user who has the private IP of 172.16.10.19, it has been assigned a public IP of 223.191.51.190. Now here, interestingly, what you observe that although the active user at the IIT Kharagpur network and at the IISc network, they had the same private IP, but while communicating with the internet, they had been assigned different public IP, and that is essential because every user in the internet should be uniquely identified by one public IP address. So that is the reason they should be assigned a separate public IP address from the block of public IP addresses which has been provided to the IIT Kharagpur network or which has been provided to the IISc. So typically when IIT Kharagpur or IISc, they register themselves with ICANN and GATE, or in India, they register themselves with Senixi or their own internet service provider, they get a block of public IP addresses, which is unique to that particular network. And one IP is assigned to the corresponding active user from that block of public IP address. Now, with this solution, we need to have a dynamic mapping between a private IP address and the corresponding public IP address. So how do we do this mapping? Now, to do this mapping, we use this particular internet middle box called Network Address Translation, or NAT. So this NAT is basically an internet middle box. We will see lots of such internet middle boxes, like the firewall is one of such internet middle box. So this middle box term is typically used to denote a device or to denote a service or method which actually resides between two networks and make an connection or make an exchange of information between the two networks. So NAT is something like that. So it resides within the gateway of an organization, and it helps in converting or translating the private IP addresses which has been assigned to the users of that particular organization with a corresponding public IP address. So here is an example, the detailed example. So in IIT Kharagpur network, I have a private IP user 172.16.10.2, and that user is active. Now that user is going to send the data packet to the outside network. Now when this user is going to send the data packet to the outside network, the packet will have the source IP as 172.16.10.2. That means the private IP of this particular device. Now this packet propagates to IIT Kharagpur network and comes to the gateway of or gateway router of IIT Kharagpur network. And this gateway router of IIT Kharagpur network, it is connected with a device or it is connected with a NAT device. Now what this NAT device does, the NAT device makes a mapping with this public IP, with this private IP to a corresponding public IP from the block of public IPs which have been assigned to IIT Kharagpur network. And it maintains a table called a NAT table. Now this NAT table basically contains a mapping between the private IP and the corresponding public IP. Now say the NAT assigns a public IP of 202.141.81.6 corresponds to this private IP 172.16.10.2. So in the NAT table, which is maintained in this device, the NAT device, it makes an entry that for the private IP 172.16.10.2, I have the corresponding public IP, which is 202.141.81.6. And it makes a translation in the packet. That means it changes the source IP of this packet, and it changes the source IP to this public IP of 202.141.81.6 and send that packet to the outside internet. Now you see, when the packet is going to the outside internet, it is actually carrying a public IP and not the original private IP, which has been assigned to the device from where the packet has been originated. Now, when the packet is traversing to the internet, it is going to the public network with this public IP address. So there would be no problem. It will be using the typical CIDR IP routing mechanism, and it will be delivered to the destination. Now, when the destination will generate the reply packet, the destination will set the destination IP as the source of IP of the packet that was originally sent to it. That means the source IP was 202.141.81.6. Now, when this network or when the target device will send back and reply, it will make this IP as the destination IP. So in the reply packet, the destination IP becomes 202.141.81.6. Now, this packet reaches to the NAT because this particular IP address is actually assigned to IIT Kharagpur network. This particular public IP is assigned to IIT Kharagpur network. That is why the internet routing, the routers, they will use the routing mechanism to route the packet to IIT Kharagpur network, and the packet reaches to the gateway of the IIT Kharagpur network. Now, when the packet reaches to the gateway of IIT Kharagpur network, the NAT again observes this packet and consults with the NAT table. Now, the NAT table contains the inverse mapping as well. So from the NAT table, it can find out that, well, for the public IP of 202.141.81.6, the corresponding private IP was 172.16.10.2. So again, it basically update the IP address from that public IP to the private IP. So the IP is updated to 172.16.10.2, and the packet is forwarded to inside IIT Kharagpur network. Now, within IIT Kharagpur network, this IP is visible to all the devices, like the routers which are there in IIT Kharagpur network. So they route this packet to the final destination, which has the private IP of 172.16.10. So this is the typical way a NAT works. So if I have a different device, say, which becomes active and that has an IP address of 172.16.10.28, so that source IP, whenever the packet with that source IP, whenever it comes to the NAT which is residing at the gateway of IIT Kharagpur network, another entry is made and corresponds to this IP. We give another public IP, which is 202.141.81.8. And whenever it is going outside IIT Kharagpur network, it gets the public IP. And in the same way, when the packet returns back, it gets the original old IP address. So this is basically the broad idea about this concept of NAT, through which the packet are basically forwarded to the outside network. Now, one major problem of this particular architecture is that in this the previous architecture, where for every private IP I was assigning a public IP, typically your requirement of public IP is still very large. That means for all the active users within IIT Kharagpur network, you need a corresponding public IP. And this assignment is dynamic. Whenever an active user becomes inactive, the corresponding entry from the NAT table gets erased. So every entry in the NAT table, they are assigned to it a corresponding timestamp. If the NAT doesn't observe any kind of activity within that time period, it erases or it deletes the corresponding entry from the NAT table. Now that way, dynamically, these public IPs are assigned to different users based on whenever they become active. Now you see that this particular approach still required a good number of public IP addresses. So typically in IIT Kharagpur network, if you assume that at any instance of time, at least 1,000 users out of the 10,000 users will be active, then you require 1,000 different public IP addresses. Now to solve this particular problem, this concept of NAT has been revised further to introduce the port address in the concept. So it is basically called a port-based NAT or PNAT. Now, in case of PNAT, or in some book, you will get the term as network address and port translation, NAPT or PNAT. Both are the same thing. Now, in case of PNAT, it uses a combination of IP address and the port number for mapping. So the IP port pair defines an end-to-end flow. So here, the NAT is applied at the flow level. So in port-based NAT, what happens that whenever a particular packet is generated and the packet is reached to the NAT, it observes the IP address and the corresponding port number. Now, whenever it is making a mapping in the NAT table, it makes a mapping with the IP address and the port number to a corresponding public IP and the port number. So here you see that for the source 172.16.10.28 with a port 80, it makes a mapping to 202.141.821.6 with a port of 12333. Now with this particular scheme, whenever the packet is going outside the network, it changes both the IP address and the corresponding port number. Now with this particular approach, the advantage is that you can reuse the same public IP for multiple connections. So here this public IP 202.141.821.6, it has been reused for both the active users, because now we are not doing the mapping at the user level, rather we are doing the mapping at the flow level with the help of the IP address and the corresponding port number. And that is why two different active users may get the same public IP. So here you can see that the private IP 172.16.10.2 and the private IP 172.16.10.28 both gets the same public IP 202.141.81.6 but different port numbers. Now here we have 65,536 different number of ports, and that is why you can actually support a large pool of users with the help of this port-based mapping. So that is the advantage of this kind of port-based map. So typically in today's network, we use this PNAT concept to support a large number of users with the help of the a single public IP and different port addresses. Now the overheads are the problems which are associated with NAT is that many of the internet protocol and services like H.323, which is a video streaming service, RCell, IRC, point-to-point transport protocol or PPTP, ICMP, many of the ICMP messages, IPsec, IP security, etc. They do not work over such internet middle boxes, particularly when the outside machine needs to initiate a connection. So if you look into our concept of NAT, you see that whenever the NAT receives a packet from a device which is inside the NATed network, that means inside the IIT Kharagpur network, during that time the NAT makes an entry to its NAT table and sends the packet outside to the outside network. Now, if the outside network first wants to initiate a connection, the outside network will not know that what is going to be the public IP interface. And at the same time, the disadvantage is that whenever it sends that packet with that particular public IP interface to the NAT will not have any information because that entry is not there in its NAT table. The entry to a NAT table is written only when it receives a packet from inside network. So that is a typical problem for NAT. That is why many of the services which need that the outside machine have to initiate a connection, that kind of particular services does not work in case of NATed network. Now there are remedies or there are solutions to do that. There are IP forwarding based mechanism. There are mechanisms where the NAT is combined with DNS to provide the support. So the DNS provides the IP address of the NAT server, which helps in address translation. So that kind of approach are typically used, but they are not suitable for all different type of applications. And the second overhead associated with the NAT is that the processing of NAT table needs to be very fast, because every packet that are coming to the NAT table, you need to make a translation at the packet header. That means you need to make a mapping with the help of the NAT table, and then you need to change that particular field to the packet header. So there is a need for modification in the packet header for all the packets. Now that is why the NAT table need to work very fast. Many a times the NAT works as a capacity bottleneck for a network, because although your network has a sufficient bandwidth, but your NAT doesn't support a large number of or a very speedy processing of packets, and that becomes the performance bottleneck. Now, in the context of NAT, I also want to introduce you this term of IP masquerading. So IP masquerading is a process where one computer, it acts as an IP gateway for a network, and all other computers, they forward the IP packets to that gateway. Now the gateway, it replaces the source IP address with another IP address. Many of the time it may become its own IP address and forwards the packet to the outside network. Now the concept of IP masquerading is typically used to hide the IP addresses of the internal computers of a network. Say for example, for a company or for an organization, they do not want to expose their internal machine to the outside network for security purpose. What they do, they use this concept of IP masquerading. So whatever packets are being forwarded to the outside network, they basically replace the IP address, the source IP address of that packet with its own IP address or some other predefined IP address, and forward that packet to the outside network. So the outside network only observes that a single machine is forwarding that packet. And that machine becomes the mouthpiece, or becomes the face of the entire network. Now here you see that the NAT actually works like an IP masquerader, because the NAT is actually doing this modification in the packet header. It actually replaces the private IP address with the corresponding public IP address. So it uses this concept of IP masquerading. Now you can actually play with such kind of masquerading toolbox. So Linux has a tool called IPMASQ. It is a masquerading toolbox where you can set this IP masquerading over Linux. So I would suggest you to play with this tool to set up it and send data packet to your machine to see that what IP address you can see at the source IP of field of that particular packet. So you can capture the packet using WhatsApp and do this analysis to see that how it looks like. So that would be an interesting exercise for you. Okay. Now that was our concept of network address translation. Now we move to the next concept that we are going to discuss today. It is address resolution protocol, or ARP. Now, before introducing you with the requirement for ARP, let me talk a bit about how IP routing is being performed, or better to say how end-to-end packet delivery in a network is being performed. Typically, we know that routing is done based on the IP address lookup. So every router, they make a lookup to a routing table to find out that what is going to be the next hop IP address, and at the same time, what is going to be the interface to which you can forward the packet to the next hop. And you get that information and then forward the packet to that corresponding next hop. So that is the kind of broad concept that we have seen. But what happens at the packet level? Now say, so we'll see both the example. We'll see the example when the packet has reached to the last mile and you need to forward to the destination. And at the same time, say the packet is in between somewhere in an intermediate router, and from there you have to forward the packet to the next hop. So in the first example, let us say that an IP packet has reached to the gateway router of a subnet. Say this is my gateway router, so the packet has reached here. Now I need to forward the packet from this router to the destination, with the packet has a destination IP of 202.141.821.78, and here is the destination machine. Now, from our concept of network connectivity, what we have learned that between two layer 3 devices. So this router is a layer 3 device, and this final host is another layer 3 device. Now, what we have seen that between two different layer 3 devices, there can be multiple layer 2 switches. So these squares are actually the L2 switches. So there can be multiple L2 switches, and these L2 switches creates a L2 connectivity in the network. And through these L2 switches, the different devices are interconnected. Now, although this router finds out that, well, the destination is in its one-half distance if we consider the layer 3, but actually in terms of physical connectivity, they are not directly connected. So this router and these machines are not directly connected. There are multiple devices. So the question is that how they are going to forward the packets in this particular instance. Now, the last hop packet delivery through the L2 switches is done based on the MAC address. Because you know that these L2 switches, they only run up to data link layer. And that is why they cannot understand IP address, or they cannot understand the processing of the IP layers. But the routers, they do not know what is the MAC address of the final destination, because the IP header of the packet does not contain that information. So if you look into the IP header of the packet, so the IP header of the packet will only contain the destination IP, that is the 202.141.821.78. But you do not know what is the MAC address of this particular machine. And you need the MAC address to use a layer 2 forwarding. We'll see in a while that how it basically done to forward that packet over the set of L2 switches. Now here is another example where the packet needs to forward it between two different routers in two different hops in a network. So that is true for every L3 hop in the internet. So the routing table gives the IP address of the next hop L3 device and the interface to which that L3 device can be reached. However, it does not give the MAC address of the next hop device. So whenever a packet is reached to this particular router, so this router in the packet, the destination IP is 202.141.821.78, and the router makes a route lookup in its CIDR routing table and finds out that, well, my next hop is 223.191.21.45, which is this router. Now, although in layer 3 they are directly connected, that means they are connected over a layer 3 link, but in physical terms, there can be multiple L2 devices. So they are not directly physically connected. So you know that, well, I will forward the packet to this interface. So eventually it will reach to this node, but how it will be being forwarded actually? Again, here you will need the MAC address to do the actual forwarding. Now the question comes that how will the router know the MAC address of its next hop device? Well, so you can note that this information is needed to populate the L2 header of the packet. Now in this context, let us look into that how this L2 header is constructed during routing. So here is an example where I have two different nodes, S1 and D1. So they have the different IP addresses. The MAC address I have just shortened as MAC underscore S1 and MAC underscore D1. And there are intermediate routers, and those routers has the IP addresses and the corresponding MAC addresses as MAC R1 and MAC R2. Now, whenever the source is constructing a packet, the source IP is the IP of this machine, which is 202.141.81.2. The source MAC is the MAC of this machine, which is MAC of underscore S1. The destination IP is the IP of the final IP destination, that is the 13.187.34.79. Now the question is, what is going to be the destination MAC? Now, many of you might think or might have a misconception that the destination MAC will be the MAC address of this machine, 13.187.34.79. But that is not true, because at every layer of the packet, whenever we put the addresses, we only consider about that layer. So in the IP layer, my final destination is 13.187.34.79, but at layer 2, this is not my final destination. This is not my next destination. My next destination is the next hop router where I am going to forward it. So the destination MAC should be the MAC of R1. But the question comes that how do we get that information? So the source IP configuration. So this is a source machine. So if you look into, you need this IP information of 202.141.210.3. Now the question comes that how you are going to get. Now, if you look into the source IP configuration of a device, it contains a parameter which is called default gateway, or sometimes it is called a gateway. So it contains the IP address of the first hop L3 router. So for example, whenever you are connected to your machine over the internet, you are ideally connected to a L2 switch. So it is something like this. Your machine is connected to a L2 switch. And after a set of L2 switch connectivity, there would be a L3 router, which is the gateway of your network. So through this L3 router, you are connected with the internet. Now, whenever you are doing your IP configuration, in that IP configuration, you need to set up the IP address of your first hop router, and the IP at this first hop router is called the default gateway. So, for example, here I have given two instances from the Windows IP configuration and the Linux IP configuration. So, in Windows IP configuration, whenever you are giving this, you can see that this is the entry for the default gateway. In Linux, it is called it is in Ubuntu, it is called the default route. So this information actually contains the IP address of the first hop router. So during your IP configuration, you actually get that information. So if you are manually configuring the IP of your machine, your network service provider will provide you all this information, the IP address, subnet mask, default gateway, at the same time your DNS server information. Or if you are using dynamic host configuration protocol or DHCP to automatically generate your IP address, then in that way, your machine will get the IP address, net mask, as well as the address of your gateway. So that way you get the IP address of the gateway. Now you have the IP address of the gateway, which is 202.141.210.3. However, as I have mentioned, that these two L3 devices are not directly connected. So the question is that, how do the network forward the packet to 202.141.210.3? Now, as I mentioned earlier, that the network needs to do a L2 forwarding. That means it has to do a forwarding based on the MAC address. Now, to do the forwarding, the protocol that is being used is called the spanning tree protocol. So we'll look the spanning tree protocol later on in details. But ideally, what this spanning tree protocol does is that it creates a spanning tree from the source across all the L2 devices which is there in the subnet. So for example, from here, it will create a spanning tree, maybe something like this. So this construct a spanning tree. So the reason for constructing such kind of spanning tree is to avoid the loop in L2 forwarding. Now with this spanning tree, say I am redrawing the spanning tree here. So with this spanning tree, the MAC frame is broadcast to all the L2 devices in the subnet. So every device in the subnet receives it. So the frame that is constructed from this machine, it will be broadcast to this entire subnet. So, and that broadcast is through this spanning tree. Now you can understand that why I need a spanning tree, to avoid the broadcast loop. Otherwise, whenever you are doing the broadcast, you will get back the same frame again and again. Now to avoid that, we use this spanning tree. Now once you have this spanning tree, over this spanning tree, you broadcast the L2 frame, L2 frame, the R2 frame. Now that way, every L2 device in the subnet, they will receive the frame. Now once a device receives a frame, what it does, that it extracts the destination MAC address from the frame and matches it with its own MAC address and see whether there is a match or not. Now, if there is a match, it accepts the frame and forwards it to the upper layer. Otherwise, it's dropped the frame. So that means at layer 3, it is not a routing kind of thing, rather it is a kind of broadcast-based protocol. So the frame is broadcast to all the nodes in the network. Now, whenever you are getting a frame at your L2 device, or your layer 2 of your protocol stack, you look into what is the destination MAC address and try to match that destination MAC address with your own MAC address. Now, if the destination MAC address matches with your own MAC address, either they will be same or the destination MAC address is a broadcast MAC address. In these two cases, there will be a match. Now, if there is a match, you accept that frame and send it to the upper layer for further processing. Otherwise, you drop that frame. And this is actually interesting. You can actually see in your network that typically in layer 2, whatever frames are being sent, all the machines in that subnet, they will receive that frame. You can test it and you can see. Although you may not receive all the frame because we have intelligent forwarding mechanism, which we'll discuss in the context of MAC layer, but at least for the first time, whenever the switches do not have any intelligence, they actually keep on broadcasting the frame to all the outgoing interface. Now, here you see that over the spanning tree, this broadcast-based forwarding at L2 requires the MAC address because I am doing the matching based on the MAC address. And why I am doing the matching based on the MAC address and not the IP address? Because the match is done at the hardware level. I am receiving all the packets over that LAN. So if I keep on sending everything at the software stack and try to do a software-based match, it will actually take a lot of processing power. That's why we do the matching at the hardware itself with the help of the MAC address. So there is a hardware match to see if there is a match between the destination MAC address in the received frame and the MAC address of this machine. If there is a match, then only we accept the frame, otherwise we drop the frame. We do it entirely thing in the hardware level. But the moral of the story is that you need the MAC address. So the question comes that, well, how this machine, although it knows that my default gateway is going to be 202.141.2102.3, how it is going to get the MAC address of this machine? Because the MAC address is not known to this particular machine. Well, so here comes the solution that it uses a protocol called Address Resolution Protocol, or ARP. So we'll see in a while how this ARP does. So the device uses this ARP to find out the MAC address of R1 and populate it in the MAC frame. Now, it uses HTTP to forward the frame to R1. Now, with the help of the broadcast mechanism, that L2 broadcast mechanism that I have mentioned earlier, the frame is forwarded to R1. Now, R1 receives this frame. Now, once R1 receives this frame, what it does, so it again look into what is my destination IP address. Now, based on the destination IP address, it makes a route lookup. So once it makes a route lookup, after doing that route lookup, it finds out that now the next hop is 223.191.21.45. Again, it needs the MAC address of this machine. So it uses ARP to find out the MAC of R1. So the MAC of R2. And populate it as the destination MAC of the frame. So here, again, the destination MAC gets updated and it becomes MAC of R2. So you see that my source IP, that destination IP doesn't get changed, but my source MAC and destination MAC gets changed. So the source MAC will be changed to, there is a typo here, the source MAC will be changed to MAC underscore R1 and the destination MAC will be MAC underscore R2. And the packet will be forwarded to the next hop using the spanning tree protocol that we have discussed earlier. So and the same mechanism will be repeated to find out the MAC address with the help of ARP at every hop, and finally the packet will be forwarded to the final destination. Here again, the source MAC will be MAC of ARP. Okay, so sorry for this time. So here you see the requirement for the ARP protocol. So whenever you are forwarding a packet, at every hop you are finding out what is going to be the next hop. You know the next hop IP. Now to find out the MAC address of that next hop IP, you need the ARP protocol. Now let us look into a bit details about this ARP protocol or the address resolution protocol. So ARP uses two different type of messages, ARP request and ARP reply, and that message particularly contains these four fields which are of interest to us. The source hardware address, it is the MAC address of the source who is requesting for the ARP reply. The protocol address, that means the IP address of the source. The target hardware address, the machine for which it wants to know the MAC address, and the target protocol address, the machine for which it wants to the IP address of the machine for which it wants to get the MAC address. Now, this ARP request, it is a broadcast in the network with broadcast IP address, that means 255.255.255.255, and the broadcast MAC address, that is FF:/FF:/FF:/FF:/FF:/FF, so all ones. Once a device receives an ARP request message where the target protocol address matches with its own IP address, then it sends back an ARP reply with its MAC address as the target hardware address. So here is an example. So this particular router, it wants to get the IP address corresponds to the machine of 202.141.86.22. So it constructs a ARP frame. So in this ARP frame, the source hardware address is MAC R1. The source protocol address is 202.141.81.2, the IP address of this machine. The target protocol address is 202.141.86.22, the IP address of the machine for which it wants to know the hardware address, and the hardware address is unknown. Now this message is broadcast over the IP packet. So to broadcast a packet, your source IP would be 202.141.81.2. Destination IP would be all ones because it is a broadcast packet, ARP request. So you need to give the broadcast IP. The source MAC is the MAC of R1 and the destination MAC is broadcast. So that way the message is broadcast, and both the L3 devices which are here, they will receive that ARP request. Indeed, all the L3 devices in the network will receive that ARP request. Now, once they get that ARP request, they see whether the target protocol address matches with its own IP address. So here you see the target protocol address 202.141.86.22. It matches with the IP address of this machine, R2. 202.141.86.22. So R3 will ignore it, and R2 will process it further to generate the reply. Now, R2 generates the reply by putting its own MAC address as the target hardware address. Now, although ARP request is a broadcast, ARP reply is typically an unicast. So in ARP reply, what happens that from ARP request, you know who has actually requested for that particular ARP data. So you put the source IP of this machine 202.141.86.22, and the destination IP is 202.141.81.2, which is the IP of this machine. So ARP reply is unicast to the machine which has actually requested for the information. Similarly, the source MAC is MAC R2, and the destination MAC we can again get the packet, which is MAC R1. You send that packet, and R1 will get that, and once R1 gets that, from this particular ARP reply, R1 can find out that, well, the MAC address corresponds to the IP address 202.141.86.22 is MAC R2. So R1 will get that information after receiving this ARP reply. Okay, so this is all about the address resolution protocol. So we got a basic idea about how ARP is used to get the MAC address corresponds to an IP address. Now we'll see another interesting protocol at the IP layer, which is called the Internet Control Message Protocol, or ICMP. Now, ICMP is basically a set of messaging protocol for internet management, error messaging, and network configuration verification. So ICMP has different type of messages that we'll see. We'll see a few examples of that, which is particularly used for network configuration monitoring to look into that whether a destination is alive or not, or many such similar purposes. Now, typically, ICMP provides a feedback when an IP message is sent. So, for example, it informs the source. So, when an IP packet is dropped from an intermediate L3 device, or check whether an L3 host is reachable. It can redirect the UDP messages. It can make a router advertisement. So, there are various purposes for which these ICMP protocols are being used. So, ICMP works on top of IP. So, we have mentioned that there are two variants of IP version 4 and IP version 6. For IP version 4, we have ICMP version 4, and for IP version 6, we have ICMP version 6. Now, ICMP broadly have two different type of messages, the error messages and the information on query messages. Now, these error messages are used to provide feedback to a source L3 device about an error that has occurred in the network. For example, you are forwarding a packet and from intermediate router, the packet got dropped. Then that intermediate router actually sends back an ICMP message informing the original host what has actually happened with the packet. And that particular message is called a destination unreachable message. So if the router cannot find out a path towards the destination, then it sends a destination unreachable message. And then this information or query message, it is used by the L3 devices to exchange information, implement certain IP-related features, and perform certain testing. So for example, echo request and echo reply. These are the two popular ICMP messages we'll see in a while. So let us see a few example use cases of ICMP. First, we will look into this ICMP echo request and ICMP echo reply. They are used in a popular tool called ping. This application is ping application is used to check whether L3 device is alive and to calculate the round trip time to that particular device. I think all of you have used ping. So if you ping a particular machine, say 172.17.160.164, so it basically keep on sending the IP packets to this machine. So you see that it sends these ICMP packets. They are basically ICMP echo request packet, and from there it actually gets the round trip time between the two hosts. So you can also find out whether that machine is alive or not. If the machine is not alive, you will get a message called the machine is unreachable. Now let us see how this ping works with the help of ICMP messages. So the ping application, it generates an ICMP echo request message towards the target L3 device. Once the target L3 device, it receives the echo request, it replies back with an echo reply. Now you calculate the round trip time by subtracting the time difference between when you have received the echo reply and when you have actually sent the echo request. So that way, with the help of this echo request and echo reply, the ICMP actually works. So whenever you are sending ICMP echo request to a machine, it will send back with an echo reply. The second popular internet application that takes help of ICMP, we'll look into. It is called traceroute. I think many of you have also used traceroute. So traceroute is used to find out the intermediate L3 device at every hop between a source and a destination. So for example, if I do a traceroute to this IP 172.17.160.164, I can get what are the different devices at every hop with certain statistics about time, that how much the maximum time that might take to reach that hop, or what is the minimum time, what is the average time. These details we get. Sometimes you will see a star because those intermediate hops have actually not responded back with an ICMP. So many times, many of the devices, the ICMP is kept blocked because of the security purpose or security reason. ICMP has a lot of security attacks which are possible. So that is why many of the organizations, they keep ICMP blocked. So the devices, they do not send back an ICMP message. They are set in their configuration. So these intermediate devices are the device from where my machine has not received any ICMP message. So that's why they keep on giving a star. For other hops, you can get the detailed information. Now, traceroute also works with the help of ICMP message. Now, here I show you how traceroute actually works. So traceroute works using two ICMP messages, ICMP time exceeded and ICMP destination. Now, to do a traceroute, what my source does, my source generates a UDP packet, a small UDP packet, with destination as the final destination D, and it uses a port. Typically, this is the port which is used by Cisco ICMP, Cisco traceroute configuration, port 33434, but that is not fixed. Your own traceroute application may use a different port. And it sets a parameter in the packet which is called a time to move, TTL equal to 1. So at every hop, whenever a device receives a packet, it first decrement the TTL. And after decrementing the TTL, if the TTL becomes 0, it drops the packet and send back an ICMP message called the ICMP time exceeded. So traceroute takes help of that particular ICMP message. So what it does, that it sets the TTL value to 1. So TTL value 1 means after the packet will reach to the first hop towards this destination D, it will decrement TTL, the TTL will become 0, and it will send back an ICMP time exceeded. The same thing happens here. So in R1, Whenever R1 receives that packet, it decrement the TTL becomes 0, it sends back an ICMP time exceeded message with its own ID. From here, S knows that, well, at first hop, I have R1 towards D. Now to get the second hop, you set the TTL value 2 and send back another UDP packet. Now, whenever this packet is being forwarded, it is received by R1. R1 decrement TTL, make it from 2 to 1, and then R1 again sends the packet to the next hop, which is R2. R2 decrement it becomes 0, and R2 sends back an ICMP time exceeded message with source as R2. So S knows that I will at 2 hop, and the second hop towards D, I have R2. Now to get the third hop, you make TTL equal to 3. R1 receives it, decrement it to 2, forward it further. R2 receives it, decrement it to by 1, make it 1 and forwards further. R3 receives it, decrement it, and it becomes 0, and R3 replies back with an ICMP time exceeded message. So that way, it knows that, well, at third hop, I have R3. Now to get the next hop, you again send another ICMP, another UDP message with TTL value as 4. So R1 decrement it, make it 3, forward it. R2 gets it, decrement it, forward it, become 2. R3 gets it, decrement it, forward it, and send it to D. Now once D receives it, D is the final destination because my destination IP matches here. Now once D is the final destination, D will receive it, and but D will see that the port number where that is mentioned in the packet at that particular port, no application is running. Now, when no application is running, D will not be able to forward this packet to a particular application. So D will now send ICMP message as destination unreachable. So from this destination unreachable message, S knows that, well, now I have reached D because the application was not running at the targeted port. So that is why it has sent this ICMP message called destination unreachable. So I have reached D in 4 hop. So that way, by periodically sending the UDP messages or UDP packets with incremented TTL value, from every hop, you get back the ICMP message, which gives you the hop information at every individual hop. So these are the two use cases of ICMP that I have shown you. ICMP actually has different other messages, so I have not covered it in this lecture. Just wanted to give you a broad idea about how ICMP works or what are the messages which are available in ICMP. So you will look into the protocol details in your textbook or the book by TCP/IP guide to look into different features which are available in ICMP or different other messages which are being supported by ICMP. And they are widely used in the network for this internet control or internet messaging purpose. So these are all about our discussion on IP layer. So today I have completed all the topics in IP layer, covering the routing and the different services which can be run on top of the IP layer. So I think we have one more lecture left at the MAC layer, which are being covered by RSC. RSC will forward you those lectures. And if you have any question regarding these lectures, please feel to post it over Piazza. We'll be happy to discuss there. So I hope all of you are staying safe. So please take care of yourself. Thank you. And thank you again for listening to this lecture. And bye.